A very warm welcome to all of you. Myself Rajan Choudhary, Professor in the Department of Civil Engineering, Indian Institute of Technology, Guwahati, instructor for the NPTEL MOOC course Pavement Construction and Technology, funded by Ministry of Education, Government of India. Today's lecture will be a part of Module 4, and it will be having a discussion on the design of unbound granular courses for flexible pavement construction. At the very beginning, I would like to acknowledge the use of text, informations, graphs and images sourced from various textbooks, codal standards, journal articles, reports, newsletters and public domain searches. Now, the mixed design in general is the best combination or the optimum combination which we can arrive using the available materials for us. So, when it comes for the unbound courses, specifically where you have your granular sub-base courses or granular base courses, the mixed design is an approach where you decide the blend of the different aggregates available with you to finally reach certain minimum requirements, which may be in terms of density or which may be in terms of the blend of the aggregates, which will be in terms of the strength which will be arrived from that particular blend. So, here it says the primary objective of the mixed design of the unbound granular courses such as granular sub-base course, wet mix macadam or water-bound macadam. These are three examples of unbound granular courses, which is what is done here is the approach of mixed design is to develop a suitable gradation and material blend. Now, the gradation, in most of the cases you will have already predefined gradations based on the numerous field exercises and research which are usable for different courses depending upon the layer thickness and the aggregate size available. So, here what you are trying to do, you are trying to look for a gradation, possible gradation and a material blend. So, what gradations, and there may be 2-3 number of different aggregate stockpiles which needs to be blended together, and this blend should provide you adequate strength and stability, drainage depending upon where we are making its use. If it is used as a drainage layer, it should serve the purpose of drainage layer, and durability of the pavement under anticipated traffic and environmental conditions. So, we try to judge the suitability in terms of this blend through different parameters of strength. Now, if we put down some of the steps which are involved in this particular one, then first of all, any mix which needs to be designed, you require the materials which are suitable or which can be used under that particular mix. So, selection of materials, and definitely you have to rely on the available resources nearby, because you cannot bring materials from very far away distances, it increases the cost. So, you will always try to come up with some blend which makes use most of the locally available materials, and before putting them to use, you need to determine the suitability of those materials, whether they are suitable for use in that particular course. Here we are talking about the unbound courses, so whether that material, especially the aggregates, are suitable for use as a granular sub-base course, wet mix macadam or a water-bound macadam. Then, as I said, because you need to target a gradation, so that gradation, for that particular achieving that gradation, you may have to combine 2-3 stockpiles of different sizes of aggregates to achieve the desired gradation. So, this blending of aggregates also forms an important part under this mixed design exercise, and this needs to be carried out as per the requirements of the gradations which may be stated by MORTH or IRC guidelines. Then, once for unbound courses the blend is finalized, then you go for the determination of this relationship between the water content and density, so as to arrive to your optimum moisture content and maximum dry density, which is required to evaluate the strength of those materials, and also useful once they are selected for their construction purposes. So, then once this relationship is derived, you obtain the OMC and MDD of these materials, you go for the determination of the strength specifically at these densities or some specified percentages of these densities. Now, we will discuss these steps here. Now, first of all, when we look into the blending of aggregates, especially as I said, the different aggregate gradations are to ensure pavement layers perform their functions effectively. Different aggregate gradations are specified by the Indian Roads Congress or the Ministry of Road Transport and Highways guidelines based on extensive research and field experience. So, they have specified that okay, for if you want, if your intended purpose is this one, it is advisable to use this particular gradation. So, you will try to target that gradation for your mix. So, and in that particular case, you may have aggregates of different sizes, which may be because of locally available materials, locally riverbed material, gravel, some alternate materials, some slag may be there, crushed gravel is there, or crushed stones are there from aggregate crushers. So, they need to be blended to arrive that particular target gradation. So, a blend of different sizes of aggregates is attempted to get the desired gradation meant for different purpose and layer thickness. Now, here you can see this is an important step. Now, for granular sub-base course, MORTH 2013 specifies 6 different gradations. These are 6 different gradations, and all are preferred for different uses, like the gradation can be there for the drainage layer, 5th and 6th are used for drainage, are preferred for drainage layer. Then we have IRCSP 42 that also recommends the characteristics of a material for use under the drainage layer. Now, here you can see, in addition to this particular one, there is a that what materials. Now, if grading 1 is to be used for a specific purpose, then the material under this category should be all 100% passing 75 micron sieve size, 75 mm sieve size, 80 to 153, 26.5, 55 to 90, 9.5, 35 to 65. So, a range is given, and also from 75 micron a material lesser than 5% is there. So, similarly, it is there for other gradations requirement also. Now, this is for granular sub-base course. Similarly, this is one which has been taken for the gradation from MORTH, which is there for wet mix macadam, which is widely preferred for use as a your base course. Waterbound macadam also, which again it gives a gradation range. There is an upper limit also and a lower limit also, and what target gradation, mid gradation can be there. So, ranges of gradation, this is one where tabular form is there. You can plot and see in which ranges your material should fall up. There will be a lower limit, this is a lower limit, the material should at least 25% pass through 4.75 and maximum 55% should pass through 4.75. So, similarly, it is given for like for 425 micron, it says that 10 to 15% should be in this range. 10% is the lowest passing and 15% is the maximum passing. Certain sieve requirements are not given for few gradings, and there are other requirements. So, different courses, different materials will have different combinations for the purpose. If I am using as a filter layer, I am using as a say filter cum drainage layer or used as a drainage layer. So, for this one, the MORTH and IRC specifies that okay, gradation 4 is to be used, gradation 6 is to be used for this particular purpose, and that is based on the extensive research and field experience gained by the different gradations. And as said, normally will prefer that your layer thickness should be at least 2.5 times of your NMS, nominal maximum aggregate size. The layer thickness should be at least 2 to 3 times of the NMS of your aggregates. Now, in field you will not have since there is a range of material which is required, but in field whatever stockpiles are available from aggregate crushers, or there may be some say it says it is quite clearly single natural or quarried material will not be able to meet. It will be quite unlikely that it meets all your one stockpile cannot give you gradations varying from say 75 mm and going up to 75 micron. Now, so it is quite unlikely that a single natural or quarried material will meet the entire gradation. 2 or more aggregate stockpiles, you can see this is an aggregate crusher, this is one stockpile getting generated, second stockpile, third stockpile, fourth stockpile. So, stockpiles means aggregates of different sizes. It will not have one stockpile will have a aggregate gradation which may be varying from 3 to 4 sieve sizes. So, and then the other one will be varying. So, there may be an aggregate which may be called as a 20 mm. So, in that particular case most of the material may pass through 1 inches, and you can say around 3/4 of inch most of the material is retained. So, it can be called as a 20 mm aggregate, 10 mm aggregate, 6 mm dust, like this way. So, all will have an aggregates in a small range compared to, and what we require is we require to need to blend these different stockpiles 20, 10, 16 or 6 dust together, so that you can finally get the gradation which you are targeting for a particular mix. Even there may be chance that one gradation is giving you a good number of sizes, but normally it is not preferred, because in that case if one stockpile is having sizes varying from very coarse to very fine, then a lot of chances are there that segregation may happen whenever the material is dropped, whether when it is stockpiled or whether when it is during the production. They have to be kept in the cold fill bins. This we will discuss when we will discuss the construction of these particular mixes. That time production and construction, during the construction part, these aggregates of different sizes are stored in these cold filled bins. Now, this is a plant. It can be a wet mix macadam plant or it may be a hot mix plant, where the aggregates which are to be used are stored in these different cold bins. Cold bins because they are at ambient temperature. Now, you have to figure it out how much of blend 1 is to be used, how much blend of stockpile 2 is used, how much third is to be used, and how much 4 is to be used. So, this is an important exercise during a mix design to figure it out or to determine what proportion of these individual stockpiles are to be used to achieve your desired gradation. So, whatever now for attempting this particular proportioning, there are different ways, but one important aspect in all cases is, regardless of the number of aggregates or the blending technique selected, the basic expression will be given by it. It says P is the percent of material passing any particular, say, sieve size 4.75, and which is arrived through a combination of 3 materials: material A, material B, material C. Now, what capital A stands here? The percent of material passing a given sieve size for each aggregate. So, if I am targeting say 4.75, then and I have 3 aggregates A, B and C. So, A, what I will write A here, how much percentage of it is passing through 4.75, that will be written here. How much percentage of second material B is passing through 4.75 has to be written here. How much percentage of third, if I have 3 stockpiles, this is a cold fill bins. So, I have 3 aggregates A, B, C. When I did the individual gradation and I try to ensure, as I mentioned, the aggregates may be in the range of some few sieve sizes. So, I will check. There may be a chance that this is 100% passing. There may be a chance this is 0% passing, that this material through 4.75 everything is retained over it. Then this is for B. For this particular material, this is for a material C, it may happen that 100% should pass through this 4.75, and this particular material, it may happen that 80% may pass through it. So, 3 stock piles of aggregates are used, and now I want to show if I combine them in a particular proportion. What proportion I am using? A, B and C, and this A, B, C has to be 1, because total when they are to be combined together, finally this is to come up as 1. So, I can just randomly I am putting up, I can use a combination where this can be 0.7, this can be 0.2 and this can be 0.1. Now, if I am using, that means 70% share is from A coming, 20% share is coming from B and 10% share is coming from C. So, this is expressed in fractions. Now, this together has to be 1 because it has to be 100. Now, or in fractions it is 1. Now, here if for this particular example, now if I want to see how much percentage is passing through 4.75, then as I said 80% is passing. So, 80 into 0.7 for the first case. Second case, it is I mentioned here 0% is passing. So, there is 0 into 0.2 because 20% share of this material, and third one 100% passing. So, 100 this C, and how much share of it is? A share of 10%. Now, this will give you 56, this value will come up as 56 and this value will be 10. So, this makes 66% passing. So, if I combine A, B and C in the proportion of 70%, 20% and 10%, then on this particular sieve, this proportion will give me a material which will be 66% passing 4.75. So, now this I have ensured for one sieve. Now, when a material is to be used for a particular layer, as I mentioned, there are 6 gradations given for granular subbase course itself, and each gradation has a range. So, it is not now for my particular use, if a range is given that your material should pass through 4.75 in the range of 50 to 70, then this particular percentage passing is okay. But if the range is given, it should be 50 to 60 only, then this proportioning or this blend is not okay. Now, this I am checking only for one sieve. I have to check it what all sieves are required in that gradation. Because there are 4-5 sieves or maybe more than that, 8 sieves may be there for a particular mix type, and for each sieve size a range is given. So, I have to ensure that for the blend which I am formulating, the combined gradation, the combined this percentage should be for each sieve should be falling in my required ranges. We will do that exercise. So, this is an important aspect which needs to be checked whenever you do this blending exercise. So, this is an important part of your mix design exercise, that always you like to see in what manner you can combine the materials, so that finally you get you are able to or combine the material or proportion the material to achieve your target gradation. Achieving the desired gradation within the specification band by blending 2 or more aggregates of different sizes is quite often attempted through trial and error. With experience, you get a good idea about it, that okay, this is a coarse array. Here, as I mentioned, if 66% is passing, I require 70% of passing. Then as C was a material where 100% was passing. So, I'll okay, if I want to increase this percentage passing, I'll increase the share of C, which was earlier 10%, I will make it 15%. So, at the share of some other material has to be reduced. So, it comes by experience, and you can just try to look which material is contributing to which particular share, coarser share, finer share, and you can adjust those percentage to arrive to a blend. So, you can attempt through trial and errors. And now various mathematical and grammatical as well as programming tools are available, through which you can attempt a quick and easy approach to get these particular blends. I will just give you an example here. Now, in this one, there is a requirement, there are 2 aggregates are given, A and B. I have for a particular work 2 aggregates with me, and my specification says that for the mix which I need to produce, the required aggregate gradation ranges are this. It says that for 12.5 mm sieve, 100% material should pass. For 9.5 mm, 80 to 100% material should pass. So, simultaneously I am writing the mid values also. I'll call it as mid values. So, my mid value here in this case 100% should pass, so it is 100 only. For this 9.5, 80 to 100, so my mid value is 90. Then it says that 4.75, 45 to 80% material should pass through it. So, approximately 17 has to be added. So, I can round it off to 62% should pass through it. Similarly, 30 to 50 should pass through 2.36. So, 40% material is mid value. Why I am mentioning here mid values? Because I will be targeting to the mid values. if I target to the mid values, hopefully what will I will arrive maybe within the range. So, I will prefer to target the mid value for my combination. Now, here in this case you have two aggregates only and you have to combine. Now, if I see these gradations, now an individual gradation of these two materials is given. Can I work out by having a single source only? So, if I think that I will not use aggregate B, I will go with aggregate A only. Whether it is possible to have it, it says that 100%, if I use 100% of it, then this material will 100% pass, this meets this requirement, 95% pass meets this requirement. When it comes to here, only 17% or 17.5% is passing, but I require a material which should 62% pass. So, using A alone will not work out. I need to reduce this percentage, I need to add another material which is finer, because here I need a percentage which is at least 62% passing and I have a percentage which is only 17.5% passing. So, and can I do it other way around? Instead of A, if I go only with aggregate B, I will not use say aggregate A, whether that is possible. Then here when it comes to 4.75, it is even at 9.5 it says 80 to 100, okay fine, 100 is there. So, the extreme limit it is there, but when it comes to 45 to 80, it says 95% is passing and I require a material which should only pass, minimum limit is 45 and maximum is 80, and here it is, if alone it is used then 95% is passing. So, alone B also cannot be used. So, now I need to do a blending of these two, so that I can, in whatever proportions A and B, I mix them or I proportion them, so that this combination should give me somewhere within this range and my target will be my mid values. Now, so here it is given. Now, for this particular one specifically what I can observe, like it comes with experience, I can observe this is a sieve size. Here you will see there is a good, in this one both of these are materials are 100% passing, here 95 and 100% passing. So, here also more or less similar is there. Here it is 17% passing, it is 95% passing, it is a good difference it is there. When it comes to this particular part, this gets significantly reduced, only 2% is passing, here 80, more than 80% is passing. So, this is one important sieve. Here you will get material only from this percentage passing, because here there is very less material available with it. So, these are important sieves which needs to be worked out when you are doing these trial and error exercises. So, if I will select say 2.36 as one of my sieves to attempt the trial and error. Now, for this trial and error what I did, I will choose, now if I have A as my proportion of material, small a is for proportion which is I am going for material A and this small b for me. Now, if this is there, then as per this equation it says how much percentage of material A is passing, 2.36, 2.2, and how much percentage of B is passing, 82.5 into B, and this is to be equals to what I desired out of it is 40%. This is my target. So, I will put my target value and my expression says A plus B is to be equals to this combinedly, this should be 1. So, I can work out, I can simplify this as this one. If I simplify this particular one, what I will get, I will show you on the next slide. So, here I just started with, important thing is you need to work out what sieves you are trying to work out. Say here 2.2A, 82.5B, as we have seen, this is for this one, this is for this one, and this is what your target was there. So, this target is mentioned here. Another is this. So, I will solve these two variables with two equations I have. So, I will solve it. What I get out of it is the value of B is determined as 0.475. So, when I get this means the share of the B material is 47%, 47.1%, and what will be the share of A will be 52.9%. So, this gives me the first trial or trial proportion which I can work out. So, the first trial which came out to me is I can use 47.1% of A material and I can use the 52.9% of B material. This is a combination. So, the proportion is to be mentioned in fraction. So, point as it is shown here for 0.471, B is 0.529. Now, with this I will try to see whether what happens at the other sieve sizes also, whether I am able to get the materials within the range. So, if I work out for 0.3 mm, see, so what it says here, I am trying to work out the percentage. Percentage here, the first one says 0.6% only, 0.6 of your 0.471 plus what is there, you have 25.2 into 0.529 and this gives you a percentage of 12.2. Now, whether 12.2 is acceptable, I will see what is the range which is required. The range says 5 to 25. So, 12.2 is within that range and the target was 15. So, it is now whether it is coarser or finer, it is coarser, because I was expecting, I wanted to target 15% material passing, but mine is only 12% passing. So, my material at this sieve is coarser. So, now with this particular blend, I am trying to see whether what I arrived with A as 0.471 and B as 0.529 is coming in the ranges. Then I saw, okay, here 100% was my requirement, here 100 came, here the range was 80 to 100, target was 90, I got 97.3. So, it is bit finer at this sieve, because I got more percentage passing. When it came to 4.75, the target was 62, I got 54, which is within the range. So, it is within the range, it is acceptable, but mine is coarser compared to what I am requiring, around 60% is my target mid value. When it came to 40 here, I exactly got 40, because this is, I solved this equation for 40 only. Now, when here it is, the target is 32, what I got was 31.4, very close to the my mid value. So, it's giving good for 1.1 mm, 1.18 mmc. When 16.6 mm or 600 micron, I will call it, here the mid value is I got 22.5 and the target was 22. So, it is again good. So, similarly, I have seen here I got 99 as my mid value, what I got is 9.4, here it was 4.5, I got 3. So, it met this proportion is able to meet out the requirement of the gradation. I can fine tune it, depending, because still all are within ranges, but as I mentioned here it is coming to be bit finer compared to what I was requiring 90%. So, if that means the share of B is more, because B is the material which is more finer here in this one. So, what I can do, I can reduce the percentage of B slightly less, I will make it less. Here what was having, I was having 52.529. So, I can make it as B as say a 0.51, and similarly I can make A as 0.49. So, with this one I can make one attempt whether this is working or not. So, in this manner, with trial and error method and with experience, you try to work out, and here important considerations are to be taken. Which material is more important? Like in certain cases you have to pay a more stress over what type of materials you have for the one which is passing 75 micron, because you will get it from 3. Here we just looked for 2 aggregates only, there may be more than 2, 3, 4 aggregates may be there. So, you need to target which one is more appropriate for you. Now, another method which is quite often used is a graphical method, which is also known as Rothfuch method, and the details are given in IRC SP 89, which is there. Especially there they have used it for the soil and granular materials stabilization using cement, lime and fly ash materials having different sieve sizes, how they can be blended to achieve a target gradation, because a gradation gives a good amount of information about the whole mix. If the gradation is dense, we can expect a higher density. If we can expect a lower permeability. If the gradation is open, we can expect that the density will be lower. We can expect that the permeability will be high. So a good amount of information is arrived from the gradation itself. Now, in this graphical method, what is attempted when this is normally done when now you have a good amount of programming and software tools, so you do this gradation very easily with those ones compared to, but this is a one where still it is practiced when you have in field, when you have 3 or more than 3 aggregates to be blended together. Now in that particular case, what exercise is to be done? First, on any graph paper, you plot a rectangular figure. Now this is a rectangular figure. This is what the target gradation you have. This is an example. Here it is given a material from 53 mm to 75 micron, which is there, and for each there is a range is given. So I can arrive the mid values also for each sieve size. So here I can say 100, this will be 97.5, this will be 70%, 50%, this will be 32, and this will be 22, this will be 12, this will be 6. So these are my mid values. Now what we do on this particular one, once you have on this graph paper, we will plot the percentage passings on our y axis, and then we will have this particular diagonal here which is there. This is the diagonal which is drawn to join these two endpoints. Here on this one you need to mark the sieve sizes on your x axis, the sieve sizes on the x axis. For marking the sieve sizes on the x axis, you need to work out the mid gradations, mid values of your required gradation. So I'll have 100%. I'll show you one example. Okay. So I have 100%. I'll have 100% here. It says so 100%. I'll mark this particular 100% over, and this will become my sieve sizes over this one. This is my 100% passing. So this is my sieve sizes here. This is a different sieve size. Just a minute. So what I'll do with respect to the percentage passing, using this diagonal line, I'll mark the sieve sizes on my x axis. So if the sieve sizes here, it is 40% is the mid value. So I'll use 40% here. 40% I'll draw this particular one. I'll extend to this one, and it is brought down, and this will give me my, this is 40% is for, sorry, there is no 40%, this is 50%. So I'll go for 50%. What I do, I'll go for 50%, I'll go for 50%, I'll drop a line down, and this 50% will show me for my 11.2. So here this is for another example, 11.2 sieve size I will mention here. So similarly all these will be marked here and plotted down. So I'll get all these sieve sizes on my x axis corresponding to these mid values of me. So it says on a graph paper, the percentage passing is first marked on y axis. X axis represents the particle size sieve size, which is to be marked based on the desired gradation. This is an example. So this desired gradation, the proportions obtained. So sieve sizes are marked corresponding to the percentage passing of the required gradation. This is done by locating the average percentage passing, which we worked out for any locating that point on the y axis. We locate that percentage passing, and then proceeding to cut this diagonal line, and then we project it down, we get the sieve sizes. So once this is done, you get your sieve sizes over the x axis for this one. Now whatever blend of aggregates you have to attempt here, it may be, say for this particular case, there may be 3 aggregates or there may be 4 aggregates. If 3 aggregates are there, I need to plot the individual gradations. I'll use these sieve sizes are given there, and with respect to the sieve sizes, I'll plot the gradation. So this gradation for A is plotted here like this way. Gradation for this second material is plotted here in this manner. So these are the gradations, which says 75 micron, 0% passing. It says for this 10 mm how much percentage is passing, I plotted this point, and for 40 mm how much percentage is passing. So, this needs to be plotted in this particular manner. So, then in this manner all sieve sizes are marked. This is gradation distributions of material A, B and C and is then drawn using the sieve sizes marked on the x axis and percentage finer marked on the y axis. So, 3 gradations I have drawn accordingly. Thereafter, since it is a graph paper, I will draw a line to represent, which I will call a balancing line. So, this is a balancing line for materials are drawn in such a manner that areas on either side of the balancing line are equal and minimum. Balancing and the gradation are equal, as well as you have the minimum also. This has to be minimum. So, if you can see, this is one gradation, this was the one gradation, B gradation going from here. Sorry, exactly it is not I. This is your aggregate gradation B. So, a balancing line of this particular one is drawn, this dotted line is drawn. What is there on the graph paper? I will see how many squares are on this side, how many squares. So, this number of squares plus this number of squares should be equal to this number of squares. Now, this makes this balancing line, and this total number of squares should be minimum. So, I'll try to make this balancing line as close to this existing. So, this one best represents the gradation B. This straight line best represents the gradation B. This dotted line best represents my gradation A. Once these 3 are there, this is again here for this particular one, this is the best gradation for my C material. Now, once you have these balancing lines drawn for your aggregate gradations, you will join these balancing lines of one gradation to the other gradation. Here this one is joined. So, this is for A, this is for B. Now, it is joined here, and where it cuts the diagonal, this is marked in this manner. And whatever you get from this percentage passing, how it is happening? When you are, this is the lower point of your balancing line of A is joined with the upper point of your balancing line B, where it cuts the diagonal, you will project it on the y axis. When I project it on the y axis, this percentage which I will get will be my material A, which is there, which is my 50%. Where it cuts, now this is the balancing line of second, this is the balancing line of third, where it cuts the diagonal here, this when projected, it came out to be this one. So, what I will say in that particular case, how much percentages of this? If this is 7 up to this particular one, then this will be 43%. And what will be the percentage of C? It will be 7%. So, my combination I got is A is 50% I have to use, B 43% I have to use, C 7%. So, it will be A as 0.5, B as 0.43 and C as 0.07. So, this proportion we arrived through this graphical method. So, when you have more number of, as nowadays you have a good amount of programming available, where you can attempt this particular one to get the best possible gradation which can be near to this one. So, this is again an explanation where it is mentioned that once you have this gradation, you have the balancing lines and you project and you get the percentages of all these 3 materials. One example has been taken up by using 3 aggregates A, B and C using this graphical method. Here you can see the ranges are given. The aggregate sizes are from 32.5 varying up to 75 micron. The range is given and then the mid values are given. So, I will take a graph paper, I will mark on my y axis the gradation. I have joined the diagonal line from here to here. What I am doing, since I will project the sieve sizes, 100% passing is my 32.4. So, 32.5 this I have written here, then 97 I'll select 97, I'll drop it to this diagonal line and I'll project it down. Here I marked my sieve size 25.4. Similarly, I checked for the 78% here, this is extended to the diagonal line, again it went down, and here I marked my 12.5 sieve size. So, in this manner all my sieve sizes are marked here. Once that is marked, I will draw my aggregate gradation. For A, what it says that 32.5 is 100% passing. So, this is again 100% passing. 25.4 100% passing, second point is here. Then it says that for 12.5 63% passing. So, for 12.5 this is my 63.5 is here. So, this point is like this way I have marked all these points and I can join all these points by a straight line. This is drawn by a rough by a free hand, you can join these points by scale. Now, once this is done for aggregate A, it is done for aggregate B also, and then it will be done for aggregate C also. So, you will have the 3 gradations of A, B, C plotted on this particular one using these percentage passing and the sieve sizes obtained on x axis. Now, once that is there, you draw this balancing line, you can put up a scale, you can see how many squares are there on this side of, if I choose this as a balancing line, how many squares are there above it and how many squares are there below it. So, you can see this is my graph paper, these many squares are below here, and over this particular balancing line, this is the area which is there above the balancing line, and this is the area which is there below the balancing line. So, what I'll preferably do here, I'll try to move this balancing line slightly up. So, I'll be able to get this either I need to go this side or this side. I'll move, because I am finding this area is slightly big than the area which is above this particular one. So, I'll bring this balancing line slightly on the lower side. So, I'll have more area over this upper side, and then this area plus this area will be more or less. So, like this way I'll draw balancing lines for all the 3 gradations by using a scale. So, here you can see one balancing line is drawn, second balancing line is drawn, third balancing line is drawn. Now, once these balancing lines are drawn, thereafter we are going to see where this is say for material A, this is the balancing line for A, this dotted is the balancing line for A, this is for the balancing line for the material B. Now, I am joining the end of this balancing line of A with the starting point of balancing line of B, and here it cuts the diagonal at this particular point, where when it was projected the percentage of A came out to be 73. Similarly, when for the next case I will see if where the end point of B when joined with the top point of C, it cuts down here. So, that gives me the percentage of B, which is 19%. So, A will be my 0.73, B will be my 0.19, and C will be my, this has to be 19%, 19 and 22%. This has to be around 4%. This is 19%. This has to be, because this needs to be 3%. This is 8%, sorry, this is 8%. So, 8 C is your 8%, 0.08. Now, this will be A plus B plus C is your 1. So, this is the way you can attempt. Now, so for different materials, when you do soil stabilization also, in that cases also you do this blending of different materials together to arrive at desired proportioning. So, this is the initial step which we normally do whenever a mixed design of these unbound granular courses is to be done, that you look into the blending of the aggregates, in what best manner different stockpiles of aggregate can be blended to achieve the desired target gradation, which is suitable for use as a sub-base course or a base course, and under that particular also as different gradations are specified by IRC and MORTH. Thank you.